Okay, we're continuing with Chapter 2 in the chemistry textbook. Previously, we went through the first two sections, which were sort of a brief history lesson into the atomic theory of matter. How matter is composed of these really small building blocks called atoms. And we talked about the history of how we developed our current understanding of the subatomic structure of atoms. So what we know about atoms is that, in general, they're composed of electrons, protons, and neutrons. I'm saying in general because there is the case of the most abundant element in the universe, hydrogen, with the most common isotope of hydrogen, actually doesn't have a neutron. It's just an electron and a proton. But in general, an atom is going to be composed of electrons, protons, and neutrons. We know that geometrically, from like a dimensional standpoint, the atom is mostly empty space, like the entire electron cloud that surrounds the nucleus. You can think about, from a scale perspective, as the size of a football stadium, with the nucleus being a marble at midfield. But now, furthermore, so we know that contained within the nucleus are all of the protons and neutrons of the atom, and then in the electron cloud, all of the electrons. Okay, but we know that an electron is about 2,000 times lighter, has 2,000 times less mass than a proton and a neutron. And then since we know that for the atom to be neutral, atoms in general are neutral, the count of the number of protons needs to be the same as the number of electrons. So it's not like you have like some huge amount of electrons compared to protons. So what that means is that pretty much all of the mass of the atom is contained within that nucleus. So as a result, the nucleus of an atom is insanely dense, incomprehensibly dense. You can think about this from the perspective of if you took the entire mass of Earth and shrunk it down to about a diameter of 2 football fields, that's the density of the nucleus. Okay, so that's our current understanding of the way atoms are structured. Okay, so in this video, we're going to go through the 3rd, 4th, 5th, and 6th sections of Chapter 2. So we're going to start by talking about atomic number, mass number, and isotopes. Then we're going to do a basic overview of the periodic table. Then we're going to talk about molecules and ions. And then finally, we'll talk about chemical formulas. So chemical formulas are like H2O, CH2, etc. Okay, and then in an upcoming video, we'll talk about how chemical compounds are named. What's the naming convention for naming any substance in chemistry? Okay, atomic number, mass number, and isotopes. All atoms can be identified by the number of protons and neutrons they contain. Yeah, that's right. You can uniquely identify any atom by specifying that the nucleus contains this many protons and this many neutrons. All right, the atomic number Z is the number of protons in the nucleus of each atom of an element. In a neutral atom, the number of protons is equal to the number of electrons. So the atomic number also indicates the number of electrons present in the atom. The chemical identity of an atom can be determined solely from its atomic number. For example, the atomic number of fluorine is 9. This means that each fluorine atom has 9 protons and 9 electrons. Or viewed another way, every atom in the universe that contains 9 protons is correctly named fluorine. So yeah, for any atom, if you know the atomic number of that atom, the number of protons in the nucleus, then because protons and electrons have the same charge, then if you know the atomic number, then you also are going to automatically know the number of electrons in that atom. Even if it's not neutrally charged, if you know it has some atom or group of atoms has a overall charge of -1, but then you know the atomic number, well, then you know that the number of electrons is 1 more than the atomic number, right? And it says here the chemical identity of an atom can be determined solely from its atomic number. Yeah, because what we're going to see as we progress through the course, when it comes to chemical activity at the atomic level, the chemistry between atoms. It's really all about the electron clouds, how the electron clouds interact with one another, how the electron clouds behave. All right, so then what does that have to do with the number of protons in the nucleus? If chemistry is all about the electron clouds, well, okay, we just talked about how the number of protons is going to directly tell you how many electrons there are, right? But then we're going to see in upcoming chapters that the number of protons is also going to tell you how the electrons are configured around the nucleus. If you know the number of protons, you're going to know how the electrons are configured, what the outermost, what we call the outermost electrons are, the valence electrons, and all of that is dictating what the chemical and physical properties of that atom are, whatever the substance is that's made up of those kinds of atoms, right? That's why the periodic table is organized the way it's organized. The elements are ordered in terms of atomic number. There's the atomic number, the number of protons in the nucleus. And and you can think about it, it's really amazing when they were first studying elements and trying to organize them and categorize them, that when you put them in order of atomic number like this, you get this periodicity in chemical and physical properties. So you come to oxygen here, then go 8 up in atomic number, you get to sulfur. Start at fluorine, go 8 up in atomic number, you get to chlorine. Start at helium, go 8 up, you get to neon. Then 8 up, you get to argon. One of the main features of the periodic table is that columns of elements called groups are all going to, in general, are going to have similar physical and chemical properties. And that's what we see. Like these are the noble gases. These are all at room temperature and pressure gases. But furthermore, chemically, they're very stable. Over here, these are all, this column these are all metals at room temperature and pressure. So they're all solid, shiny, ductile metals. But furthermore, chemically, they're all reactive metals, unstable. As opposed to here, these are metals, copper, silver, and gold. But as we know, these metals are stable, not very reactive. Okay, but you can think about how, anyone can, if they're discovering elements, can just organize the elements based on their similarity in physical and chemical properties. There's nothing special about that. Oh, you discover an element. If it's a gas, if it's like this, put it into that group. Well, anyone can do that, right? But it didn't have to be the case that when you ordered these elements based on the number of protons in the nucleus, that you also got this synchrony, this alignment in physical and chemical properties this way, periodically. That didn't have to happen, right? Okay, and so I just touched on it a little bit, but in the upcoming chapters, we're going to learn more specifically exactly why this periodicity in terms of the atomic number happens. It's all about how the atomic number is telling you the number of electrons in the atom, but then it's also going to be naturally telling you how those electrons are arranged, how they're configured, what are the outermost electrons, the valence electrons. And that's what's dictating the physical and chemical properties. Okay, now, so you can see it says every atom in the universe that contains 9 protons in the nucleus is correctly named fluorine. So, yeah, of all of this information here, these characteristics shown in the periodic table about a given element, arguably the most important is the atomic number. And the reason is because it's what we're going to see is you can have a lot of this stuff change. You can have different oxidation states, different mass numbers, different electron configurations. But as long as the atomic number is the same, then you're dealing with iron, the element iron, no matter what. Right? So this is a very important distinguishing characteristic, the atomic number of an element. It's actually not enough to uniquely identify a given atom. And this can get a little bit confusing. So this is enough, the atomic number, to uniquely identify an element, but not in any given atom. Okay, so what do I mean by that? Let's keep reading. Okay, the mass number, A, is the total number of neutrons and protons present in the nucleus of an atom of an element. Okay, except for the most common form of hydrogen, which has one proton and no neutrons, all atomic nuclei contain both protons and neutrons. In general, the mass number is given by, so the mass number, like the atomic number, is going to be an integer, a positive integer, and you just count the number of protons and count the number of neutrons and add those together, and that's the mass number. All right, now why is it called the mass number? So why mass? Because the electron weighs about 2,000 times less than the proton and the neutron. If we come here, right, the proton and the neutron weigh close to the same amount. There's a little bit of a difference. 1.67262 times 10 to the minus 24, 1.67493 times 10 to the minus 24. Okay, but the electron weighs about 2,000 times less than the proton and the neutron. So what that means is that if you're going to calculate the mass of an atom, and you start by adding the masses of the protons and the neutrons, then you want to say, okay, I want to factor in the mass of the electrons as well. The electrons are only going to change the mass that you calculated of the protons and the neutrons summed together based on like the third or fourth decimal place, right? So effectively, it's the count of the number of neutrons and protons is that's the mass of the atom. Okay. The number of neutrons in an atom is equal to the difference between the mass number and the atomic number. Yeah, so if you have any of this information, in particular 2 of the 3 values, then you can solve for the other value, right? If you're dealing with an atom and you know the number of neutrons and you know the mass number, then you can solve for the atomic number. If you're dealing with a certain atom and you know the mass number and atomic number, you can solve for the number of neutrons, right? And then it says, note that all of these quantities here, the mass number, atomic number, number of neutrons, these are all integers. These are counts. Okay, atoms of a given element do not all have the same mass. Most elements have 2 or more isotopes, atoms that have the same atomic number but different mass numbers. For example, there are 3 isotopes of hydrogen. One, simply known as hydrogen, has 1 proton and no neutrons. The deuterium isotope contains 1 proton and 1 neutron. And the tritium has 1 proton and 2 neutrons. Yeah, so that's why to uniquely identify a given atom, so we're talking about an actual atom. If you zoomed in and looked at this one atom, here's the nucleus, here's the electron cloud. It's not enough to just give the atomic number. Yes, with the atomic number, you can really narrow it down because that gives you what the element of that atom is, what kind of element it is, which is, you're the vast majority of the way there to constraining what you're looking at once you know what element it is. Okay, but it's not enough to fully constrain that atom because you can have different isotopes of the same element, right? Like they just talked about. You could be, if you zoomed in on an atom and you were given its atomic number is 1, so you're dealing with the hydrogen, with hydrogen, the hydrogen element, but you also need you could be given either the mass number or the number of neutrons. Either way, you'll be able to solve for the number of neutrons, right? If you're given the mass number, then just subtract the atomic number, you get the number of neutrons. Then you know what isotope of the hydrogen atom you're dealing with. Then you fully constrained that atom. Okay, so that's a little bit confusing at first, that you to be able to distinguish between, an atom and an element technically aren't the same thing. You can have a tendency when you're first learning chemistry to look at the periodic table and see, okay, these are all hydrogen atoms, right? This is the hydrogen atom. This is the helium atom. This is the lithium atom. Technically, that's not correct. This is the element hydrogen. This is the element helium. There's different types of atoms that are the element hydrogen, different isotopes. Okay, now you might be thinking, well, okay, if I have a sample of gold, if I've got a gold bar, well then what type of isotope is that gold bar? How do I know what type of atoms of gold a certain gold bar is made of? Well, the way it works is if you're looking at some substance in nature, some solid, liquid, or gas substance, just in general, you're not looking atom by atom. You're looking at it from a macroscopic scale as a substance. Then, like a bar of gold is going to naturally contain a mixture of its isotopes. It's different isotopes of the gold atoms, right? All the different isotopes are gold. They're all gold atoms. They're just technically different atoms. They're different isotopes. But if you have a bar of gold, it's going to contain this natural mixture of the different gold atom isotopes. Now you might say, well, okay, so it's like an even distribution. No, it just depends. The relative abundance of different isotopes of the different elements is unique to each element. And that's why it can be easier to, when you think about the term element, it kind of goes in line with like thinking about a substance. The term element is like from a macroscopic perspective. I have a bar of gold. That's the element gold. Whereas from an atomic perspective, it's not like you can't use the term element from an atomic perspective, but it's like you don't really look at an atom of gold and say that's the element gold. That's it. You don't look at an atom and say this is an element. You really would more say this is an atom of the element gold with this mass number, or this number of neutrons in the nucleus, this isotope of gold. You look at an atom, any atom, and say, okay, this is which isotope of which element. Okay, the accepted way to denote the atomic number and mass number of an atom of a certain element is as follows. So yeah, if you want to just generally specify the atomic number or mass number of a certain element, you want to put this into a paper, put this into a presentation, just specify one or both of these two numbers. The general way to do it is you put the chemical symbol, like iron, you put the chemical symbol, and then as sort of a superscript on the back side of the chemical symbol, you would put the mass number, and then as sort of a subscript on the back side, you put the atomic number. So that's the general convention that's used to, if you want to communicate to someone on paper or like in a presentation, the mass number, atomic number, or both of a certain element, right? So you would specify the isotope of hydrogen, that atom that has no neutrons in the nucleus, this way. You would specify the deuterium isotope of hydrogen, which has one neutron in the nucleus, this way. And same with tritium, which has two neutrons in the nucleus. And you can see, looking at these symbols, it tells you how many neutrons there are in the nucleus, because it gives you the atomic number as the subscript. And then the superscript is the mass number, which is the number of protons plus neutrons in the nucleus. So if you subtract these two numbers, you're going to get the number of neutrons in the nucleus. So this tells you everything you need to know about this specific atom, even the number of electrons, because if it's a neutral atom, then you know the number of electrons is going to be equal to the number of protons, which are given as the atomic number. Okay, as another example, consider two common isotopes of uranium with mass numbers of 235 and 238 respectively. So yeah, we can think about with this symbology here, so the chemical symbol here, if you have the atomic number, then that specifies what the chemical symbol is. These two go hand in hand. If you know the chemical symbol, then you know the atomic number. Or if you know the atomic number, then you know the chemical symbol. But that's not necessarily the case with the mass number. Just because you know the mass number, that doesn't guarantee that you can say for sure what the chemical symbol is, what the element is, right? Because, for example, you have isotopes of helium. So helium is going to have two protons in the nucleus. There's isotopes of helium with 2 protons and 1 neutron in the nucleus, so that's atomic or mass number 3. But we just saw there's the tritium hydrogen isotope has mass number 3. So just because you have the mass number, that doesn't guarantee that you know what the element is. But if you have the atomic number, that does guarantee what the element is, the chemical symbol is. Right? So with uranium here, with any uranium isotope, you're going to have a 92 as the atomic number. But with different uranium isotopes, you have different mass numbers, which means different numbers of neutrons in the nucleus. So it says the first isotope of uranium is used in nuclear reactors and atomic bombs, whereas the second isotope lacks the properties necessary for these applications. Interesting. With the exception of hydrogen, which has different names for each of its isotopes, isotopes of elements are identified by their mass numbers. Thus, the preceding 2 isotopes are called uranium-235 and uranium-238. Yeah, so we saw that the different hydrogen isotopes actually got their own unique names. The most abundant isotope, the hydrogen atom with no neutrons in the nucleus, is just called hydrogen. But the isotope with mass number 2 was called deuterium, with mass number 3 was called tritium. But in general, isotopes of atoms don't have their own unique names, and so the naming convention is you just state the element and then right after state the mass number. Uranium-235, uranium-238. Okay, the chemical properties of an element are determined primarily by the protons and electrons in its atoms. Neutrons do not take part in chemical changes under normal conditions. Now, you might look at this sentence and say, well, wait a minute, we just saw the uranium-235 and 238 were different. One was used in nuclear reactors and atomic bombs, whereas the second lacked the properties to be used for these applications. Okay, that's not chemical properties. These are nuclear properties. When we think chemical properties, we're thinking about the electron clouds and how they interact, how they behave within the same atom and interact with other atoms. Okay, so thinking about chemical properties, that the electron cloud, the chemical properties of an element are determined primarily by the protons and electrons in its atoms. Neutrons do not take part in chemical changes under normal conditions. Therefore, isotopes of the same element have similar chemistries, forming the same types of compounds and displaying similar reactivities. Okay, so in general, we can think about how just because you have 2 separate isotopes of the same element, chemically, not from a nuclear perspective, chemically, there's not going to be much difference. Okay, example 2.1 shows how to calculate the number of protons, neutrons, and electrons using atomic numbers and mass numbers. So yeah, we're going to work a bunch of examples like this. It's really simple. Remember, one thing you want to keep in mind is you automatically know, if you know information about the number of electrons or the number of protons within an atom, then you can determine either one. So if all you know is information about the number of protons, then that's going to dictate the number of electrons if the atom is neutral or if it has a -1 charge, and vice versa. Okay, the periodic table. So we're going to talk about the basic fundamentals of the periodic table here, and then in upcoming chapters, we're going to go into a lot more detail, in particular chapter 8. Okay, more than half of the elements known today were discovered between 1800 and 1900. During this period, chemists noted that many elements show strong similarities to one another. Recognition of periodic regularities in physical and chemical behavior and the need to organize the large volume of available information about the structure and properties of elemental substances led to the development of the periodic table, a chart in which elements have similar chemical and physical properties are grouped together. Yeah, so the main feature of the periodic table is that columns, which are called groups of elements, have similar physical and chemical properties. But this in and of itself is not special, because anyone can, oh, look, I discovered a stable gas, go put it in the stable gas group, right? What's so special about that? What's special is that this alignment in properties happens when you order the elements with based on a certain property that on the surface wouldn't necessarily have anything to do with chemical and physical properties. So when they were first learning about the discovering elements and trying to organize them, they originally organized the elements based on atomic mass. They could accurately measure the atomic masses of the elements. And when they organized them that way, they were still remarkably successful at getting this alignment in chemical and physical properties. The 8th heaviest element, oxygen, then go to the 8 heavier elements, you get the sulfur. Start at helium, go 8 heavier elements, you get to neon, go 8 heavier elements, you get to argon, and these properties are lining up, which isn't very intuitive. I mean, in our experience in life, we don't, if there's something is heavier, that doesn't dictate its physical and chemical properties. If I've got like a little bit of water or a big vat of water, so that doesn't have anything to do with that it's water, that it's liquid, that it's just that it's physical and chemical properties, right? The amount of something doesn't have anything to do with physical and chemical properties in our experience of life, right? So the fact that ordering based on mass number was remarkably successful at getting this alignment here, these groups like this, didn't have to happen. That was very interesting. Now we know today that it's technically not the mass number, but the atomic number. But you can see why there was still the mass number happened to work out pretty well, because like the atomic number and the number of protons and the number of neutrons usually are about the same. Carbon's going to have 5 or 6 neutrons. Nitrogen's going to have 6 or 7 or 8 neutrons. But it's not foolproof, though. That was a big question. So organizing based on atomic mass, why did argon weigh a little bit more than potassium? According to atomic mass, potassium should be in this slot and argon in this slot. And so upon further inspection, they saw that it was really more about the number of protons in the nucleus. That was the right way to order the atoms to get the elements to get this alignment. Okay, so but you've got groups, the columns in the periodic table. The rows are periods, and that periodicity comes from if you start at oxygen and you progress through the periods. That's where you get that periodicity, that alignment in physical and chemical properties in general. Let's see. So the columns are they're groups or families. Okay, now what else? Let's see. So everything to the left of this line here it gets a little bit ambiguous with some of these unknown elements as far as what exactly their chemical and physical properties are. But everything to the left of this line are metals, except for hydrogen. Hydrogen would come over here. Okay, so yeah, note that these two periods here, the lanthanides and the actinides, get squeezed in, so I can show you that. Yeah, there we go. That's technically more what the periodic table looks like. So everything to the left of this line are metals. All of this, except for hydrogen. The vast majority of the elements in the periodic table are metals. And a metal is exactly what you're thinking it is. At room temperature and pressure, most of these elements are going to be these shiny, ductile, malleable solids that are good conductors of heat and electricity. In general, that's the case. I mean, they're all metals, but there are special cases of so mercury is just going to be a liquid at room temperature and pressure, but it's still a metallic liquid. It's this shiny, metallic-looking liquid. Okay, now when you get to the transition point of this line, you have what's called the metalloids. These are going to have intermediate properties between metals and non-metals. That's the big idea with silicon. It's perfect for what it's used for with computers. Okay, now then the non-metals are, so you've got a lot of the non-metals at room temperature and pressure are gases. These are all gases here, the noble gases. These are all gases except bromine's a liquid. You have nitrogen and oxygen are gases. Hydrogen's a gas. Okay, then copper, phosphorus, sulfur, selenium are solids. So thinking about the solid properties of a non-metal, it's going to be like dull, not shiny, brittle. It's not going to be a good conductor of heat and electricity. Okay, now when we think about how most of the non-metals are gases at room temperature and pressure, then but like most of the metals are solids, then what that indicates is that in general, non-metals are going to have lower melting and boiling points than metals. Okay, so a metal is a good conductor of heat and electricity, while a non-metal is a poor conductor of heat and electricity. A metalloid has properties that are intermediate between those of metals and non-metals. Okay, the majority of known elements are metals. Only 17 elements are non-metals and 8 elements are metalloids. From left to right across any period, the physical and chemical properties of the elements change gradually from metallic to non-metallic. Yeah. Okay, elements are often referred to collectively by their periodic table group number. So you just say group 1A or group 2A. You just specify the group number. But there's also different categories based on they'll name groups. So this is the alkali metals. These are all the alkali metals at room temperature and pressure are going to be these solid metals, shiny, ductile, etc. But chemically, they're also going to be very, very reactive. Go look at YouTube videos where they show how reactive alkali metals are. Now, you might be saying, well, wait a minute, sodium, isn't that like salt? That's not a metal. Well, no, that's sodium combined with chlorine in an ionic bond, an ionic compound. No, sodium by itself is a metal. All right, you've got the alkali earth metals, the noble gases. Let's see, these are all the transition metals here. These are the lanthanides, the actinides. So there are different categories that aren't solely based on just the same column, the same group. And we'll learn more about these different categories in upcoming sections. Okay, molecules and ions. So the title of this chapter is Atoms, Molecules, and Ions. The first 4 sections, the history of atomic theory, the development of our understanding of the subatomic structure of atoms, and then everything we just talked about so far in this video was mostly about learning about atoms. And so now to finish off the title of this chapter, now we want to talk about molecules and ions. Okay, and so what you want to think about is if you take any substance in the universe, substances in nature, or even in industries, things you synthesize, whatever, any substance or like any mixture, whatever. Okay, if you zoomed in on that substance and could look at it at the atomic level, and you could cycle through the solid, liquid, and gas states of that substance, because any substance at the right conditions of temperature and pressure can exist in all 3 states. You can vaporize gold. It takes a lot of heat, but you can do it. You can freeze the noble gases. You can freeze oxygen, whatever. Right? So if you took any substance in any circumstance and you could zoom in and look at the atomic structure, yes, we're going to learn throughout this course, and if you go past this course, just looking into materials science, that there's a lot of different sort of circumstances that you would see when you zoomed in. There's different kinds of solid structures, right? There's different types of bonding. Okay, but however, in all circumstances, no matter what's going on at the atomic level, if you're looking at a metallic bond, some sort of covalent network solid, etc., there's really only 3 distinct types of atomic features that you'll see, to where these features get their own unique name and their own dedicated description. Okay, that's atoms, molecules, and ions, the title of this chapter. Now you might be thinking, well, wait a minute, what about, like there's covalent bonds, there's, different crystal structures, etc. That's true. But still, the covalent bonds are just bonds between atoms. And that creates these groups of bundled atoms called molecules. A lot of the crystal structures you would see, or if you vaporized these crystal structures, are formed between ions. These ions bonded together to create these ionic compounds. All right, now, maybe you could say that a metallic bond, so like pure iron, for example, is kind of its own special feature, because we're going to learn about metallic bonds. You've got the nucleus is joined together in a crystal lattice structure, and then around the lattice is this sea of electrons. So the electrons aren't, once the structure is created, the electrons aren't local to the initial iron nucleus that they started with, and that's why the metals can conduct electricity and heat so well. Okay, but still, a metallic bond is not going to be its own distinct type of identifiable feature. You can look at the atomic structure of a substance and say, okay, there's atoms, there's ions, or there's molecules, right? You could sort of look at a metallic bonded structure and say sort of like the atoms all came together and now they're all sharing the electrons as this big unit. It's sort of like a super covalent bond, something like that. It's like this big super atom. But in general, no matter what, when you look at a substance, you zoom in on a substance, the main distinguishable types of features you can point out and use to put into categories and kind of use as hinge points, as anchor points, are, okay, you have atoms, or you have molecules, or you have ions. Okay, so we know what an atom is, all right? Of all the elements, only the 6 noble gases in the last column of the periodic table exist in nature as single atoms. For this reason, they are called monoatomic, meaning a single atom gases. Most matter is composed of molecules or ions formed by atoms. Okay, yeah, so when you zoom into any substance, in general, there's going to be one of two cases you're going to see. Okay, and we can view these cases from the perspective of the chemical formula of that substance, which is just like H2O. The chemical formula gives you what the substance is composed of, and also like a sense of the proportions of what it's composed of. H2O, there's 2 hydrogen atoms for every 1 oxygen atom. Okay, when you zoom in on a substance, there's going to be one of 2 scenarios in general. The first scenario is you'll be able to identify molecules. So you'll be able to identify that you're looking at a molecular substance. So a molecule is an aggregate of at least 2 atoms in a definite arrangement held together by chemical forces, also called chemical bonds. So you'll just be able to identify these distinct bundles of atoms clearly. If you zoomed in on water and you looked at it in the solid, liquid, gas state, you'll be able to clearly identify, well, look, I can see these bundles of elements grouped together, these trios of elements grouped together with one of the oxygens and 2 of the H's, clearly. Okay, and whenever you see this, a molecular substance, its chemical formula, the formula you use to describe the composition of that substance, is based on the molecules that it's made of. So with water, you would say, look, I can see there's 2 hydrogens and 1 oxygen in each of these water molecules, so that's the chemical formula. Okay, and what it's saying here is that, so of all the elements in the periodic table, if we think about elemental forms of substances of these elements, so like the elemental form of oxygen, so like if you had a big tank of oxygen gas, or a bar of iron, a bar of gold, there's only one group of elements that at that atomic level it exists on its own as a single atom. That's the noble gases. So like if you zoomed in on oxygen gas, there's different elemental forms of oxygen gas, but most commonly when you zoomed in, you would see O2 molecules. These two oxygens bonded together, and that's what you would see flying around, these pairs of oxygens. But there's also O3. Right? Only with noble gases, in general, I mean, no, there's special conditions of temperature and pressure where you could actually see this with oxygen as well. But in general, only with noble gases would you zoom in and see, just flying around, you would see these krypton atoms, these fully intact krypton atoms just flying around on their own. You wouldn't see any molecules when it comes to noble gases. Now you might be saying, well, wait a minute, like what about iron? If you zoomed in on iron, aren't all the iron atoms on their own? Well, no, that's a little bit different. So if you solidified, if you froze krypton gas, what you're going to see is you would still be able to see the intact krypton atoms with their electron clouds, their fully intact electron clouds, just sort of bundled together, stuck together. If you zoomed in on iron, you're going to see this like synchronous lattice structure, crystal structure, with the full sea of electrons. The electrons have left their original iron cores. The iron atoms aren't really intact anymore. You're not really seeing distinct iron atoms that haven't really changed. This only happens in general. There's special cases of temperature and pressure where you could have like oxygen gas with just a single oxygen atoms, but in general, this only happens with noble gases. If you zoomed in on elemental forms of substances with any of the elements in the periodic table, if it's not a noble gas, you're going to be seeing the vast majority of the time, unless it's a special case, you're going to be seeing molecules. Or you're going to be seeing, if it's not molecules, you're going to be seeing some sort of like a crystal type structure. And so you might be wondering, well, what's the crystal type structure? It's not a molecule. So what exactly are we talking about there? Like, why can't we identify like iron as a molecule, let's say? Or, okay, sodium chloride. It's like a salt crystals, right? I mean, don't we write that as NaCl? It's like, these NaCl molecules, right? Well, no, it's very different, because what you want to think about is when it comes to these lattice structures, these like infinite lattices that you don't call molecules. It makes no sense. We could not say with NaCl, again, you've got these sodium and these chloride and sodium ions sort of bonded together in a crystal structure. Okay, it would make no sense to write the chemical formula for an ionic compound or any kind of like that lattice structure, like iron, for example, to write it as something like Na2Cl2, or write the chemical formula for iron as like Fe3. But with molecules, you can do something like this. Like you could say H2O2, and this makes perfect sense. But this does not make sense with like Na2Cl2. Why not? Because, okay, with the infinite lattice, I could just as easily put Na3Cl3, Na5Cl5, Na10Cl10. With the iron, I could just as easily put Fe10, Fe50. With H2O2, I'm clearly identifying, like, okay, so you might say, well, why can't we just put HO then? Well, no, because you can clearly see the individual molecules. It's two hydrogens and two oxygens. They're distinct. So, no, you wouldn't want to put this, because it's not the individual. If you vaporized H2O2, you would see these bundles of two H's and two oxygens flying around. You wouldn't see bundles of just a single hydrogen and an oxygen. But with Na2Cl2, no, you just reduce it down to the simplest integers. That makes the most sense. That's all you can say. It makes no sense to say Na2Cl2. You just want to say, look, no, it's one part, there's one nitrogen or sodium atom for every chlorine atom. Here, Fe3, don't put that. Just look, it's iron, right? So you see the difference. You see the difference. If you zoomed in on any substance, no matter what it is, in nature, in industry, synthesized, whatever, you're gonna when you zoom in, you're gonna see, okay, this is either a molecular substance or it's not a molecular substance. It's gonna be one of the two, molecular or not molecular. Okay, and again, a molecule is this aggregate of at least two atoms, so it needs to be at least two atoms. So you wouldn't consider, if you zoomed in on a noble gas and saw the individual argon atoms flying around, you wouldn't call that a molecule. Okay, held together in a definite arrangement by chemical forces. Yeah, in particular, it's you think about covalent bonds when it comes to molecules, and with crystal structures, you typically think about ionic bonds or metallic bonds. But I don't want to go too far there because there are covalent network solids, these networks of molecular units all covalently bonded together to create a structure. So, but in general, that's the way you think about it. Molecules, it's covalent bonds. The lattice structures are metallic and ionic bonds. Okay, a molecule may contain atoms of the same element or atoms of two or more elements joined in a fixed ratio in accordance with the law of definite proportions. Yeah, so it can be the same element or different elements. You have H2O or you have O2, H2, right? And in accordance with the law of definite proportions, what they're saying there's no, if you have H2O, you don't think about you can pump a bunch of oxygen gas into the H2O and increase the oxygen concentration to where now you've got more concentrated water that's H2O2. No. H2O2 is a completely different substance than H2O is. Hydrogen peroxide can be poisonous, whereas H2O, water, is like the key to life. Okay, thus a molecule is not necessarily a compound, which by definition is made up of two or more elements. Yeah, so remember, a compound is a substance that it's made up of two or more types of atoms, well, two or more elements. You can have different types of atoms, different isotopes, but two or more elements. Whereas something like, if you have a substance made up of only one type of element, that's an elemental form. And so, yeah, you can have molecules that are compounds or pure elements. Hydrogen gas, for example, is a pure element, but it consists of molecules made up of two H atoms each. Water, on the other hand, is a molecular compound that contains hydrogen and oxygen in a ratio of two hydrogen atoms and one oxygen atom. Like atoms, molecules are electrically neutral. Yeah, so in general, you think about molecules like atoms as electrically neutral, but we're about to talk about how you can have atoms that aren't neutral, but you just don't call them atoms anymore. You call them ions, but they still are atoms. Atoms in the sense that it's just a nucleus with an electron cloud, right? And it's the same idea with molecules. You can have a molecule that's originally neutral like an atom, but it can become charged, and in which case you just call it an ion. Okay, the hydrogen molecule, symbolized as H2, is called a diatomic molecule because it contains only two atoms. Other elements that normally exist as diatomic molecules are nitrogen and oxygen, as well as the halogens, the second to last group. So fluorine, chlorine, bromine, and iodine. Of course, a diatomic molecule can contain atoms of different elements. For example, hydrogen chloride and carbon monoxide. The vast majority of molecules contain more than two atoms. They can be atoms of the same element, as in ozone, which is made up of three atoms of oxygen, or they can be combinations of two or more different elements. Molecules containing more than two atoms are called polyatomic molecules. Like ozone, water, and ammonia are polyatomic molecules. So these these adjectives that they're using here, the monoatomic, diatomic, and polyatomic, okay, we're using them here in this section as adjectives to describe molecules or ions. We're going to talk about ions in a second. Okay, so you can have like a monoatomic, diatomic, or polyatomic molecule, or a monoatomic, diatomic, or polyatomic ion. And what these adjectives are referring to, this can be a little confusing at first, is the total number of atoms in that molecule or ion. The total number, not the total number of different types of atoms in terms of the different types of elements. No. Just strictly count the atoms. So this is confusing because you see something like NH3, and it's easy to say, okay, this is diatomic, right? It has nitrogen and hydrogen. No, there's 4 atoms here. If there's more than 2 atoms in the molecule or the ion, you call it polyatomic. That's why O3, it's easy to say this is monoatomic. No, this is polyatomic. There's 3 atoms in this molecule. It's just a single atom, like they said the noble gases. If you zoom in on the noble gases, it's a monoatomic substance. It's these single atoms, right? We can think about, based on the definition of a molecule, that there is no such thing as a monoatomic molecule, because you need at least 2 atoms. You don't consider, when you zoom in on krypton and see the krypton atoms, you don't consider these molecules. So a molecule is going to be diatomic at least. Most of the time, polyatomic. Water is polyatomic, 3. Okay. Now, ions. Okay. So you zoom in on a substance, solid, liquid, or gas substance. You're looking at it at the molecular level. You can cycle through the different states. It's solid, liquid, and gas states just to get a full view of the substance. Once again, there's 3 main distinct types of atomic-sized features that you'll see. You'll either see these features distinctly, or it will just be like a slight variation of these features. You could always like springboard off of these features as sort of anchor points. Okay, you're going to be seeing atoms, right? Atoms or molecules, so which are like atoms, these groups of atoms bonded together, or you'll be seeing ions. Okay, so what is an ion? An ion is a neutral atom or molecule that has had 1 or more electrons completely removed from it or completely added to it. That's an ion. I'll say it again. An ion is, you start with a neutral atom or a neutral molecule. Okay, and then from there, you either completely remove or completely add 1 or more electrons, and then you have an ion. Okay, so what you want to think about is, so we're not, in this process of creating an ion, we're not changing the nucleus. We're not, and specifically the atomic number. We're not changing the number of protons. So we're not changing, with ions, we're not changing the element. That's why when it comes to ions, you're going to say, so if you have Na, sodium, well then if you remove an electron to create a cation, it's the sodium cation. It's still sodium. You're not changing the element, right? If you started off with a neutral OH bonded together, and now you create an ion, you still have an oxygen and an H element bonded together, but now it's just an ion, which the main characteristic of the ion being that you don't have the same number of total protons and total electrons in either the atom or the group of atoms bonded together. If you added up all of the protons in oxygen and all of the protons in hydrogen, and then you add up all the electrons in the electron cloud, here you're going to have 1 more electron. That's why it's -1 charge and not neutral. Here, if you added up, well, in this case, it would just be the total number of protons in sodium, 11, the sodium nucleus. Well, since the charge is +1, that means you know that there's 10 electrons in the electron cloud. Here would be oxygen has 8 protons, hydrogen 1. So there's 9 protons here. Well, since this has a charge of -1, that means you know that these total clouds here to get the total electron cloud aggregate here together in this covalent bonded electron cloud, there's 10 total electrons. Okay, now we talked about how the atomic number in general is going to dictate the chemical behavior and properties of an atom. And in general, that is true. However, it still is the case that these are two different atoms. The neutral atom or molecule and its corresponding ion are different. They're closely related, same element, but they are different. They are different. A neutral atom or molecule and its ion are going to have different sizes because you've lost or gained an electron into that outer cloud. It's going to get bigger, or it's going to shrink, right? Sodium chloride, you've got these bigger chloride anions surrounded by these smaller sodium cations because sodium has lost an electron. Chlorine has gained an electron. Okay, but furthermore, so you do have the same number of protons in the nucleus. That's true. But what makes the atomic number so closely associated with chemical properties is that, like for neutral atoms or molecules, the atomic number is dictating how many electrons there are and then how they're like built up, the electronic configuration, the electronic structure, which then dictates the chemical behavior. Well, with an ion, you've removed one of the electrons. You've changed that electronic structure. And then with the ion now, you're dealing with this unbalanced charge, right? So how the electron cloud is going to react in different circumstances when it comes to an ion is just going to be different. It's going to have different chemical properties than the original atom. But again, they still are very closely related. It's still the same type of element. So, okay. An ion is an atom or a group of atoms that has a net positive or negative charge. The number of positively charged protons in the nucleus of an atom remains the same during ordinary chemical changes, called chemical reactions, but negatively charged electrons may be lost or gained. The loss of one or more electrons from a neutral atom results in a cation, right, positively charged. For example, a sodium atom can readily lose an electron to become a sodium cation, which is represented by Na+. Yeah, and so you start off with 11 protons, 11 electrons. You lose an electron. Now you have one more proton than electron. Still the same number of protons, so it's still sodium, but now it's Na+. There's one more proton than electrons, the Na+ ion. And then same idea from the other perspective. On the other hand, an anion is an ion whose net charge is negative due to an increase in the number of electrons. A chlorine atom, for instance, can gain an electron to become the chloride ion. Yeah, gain an electron, it's still chlorine, still 17 protons, but now you have one more electron than proton, so it's we call it the chloride ion. Sodium chloride, NaCl, ordinary table salt, is called an ionic compound because it is formed from cations and anions. So yeah, in a lot of cases, it's energetically favorable in nature, in industry, like in chemical plants, whatever. It's energetically favorable for these originally neutral atoms. If they kind of get associated with each other, they're saying, okay, look, no, it's more stable if I become a cation and the other one becomes an anion, and they come together to form this neutral bond, this ionic compound. All these ions come together and neutralize the charge and create this big neutral compound of ions bonded together. That's energetically favorable in a lot of circumstances, right? In normal circumstances, you're not going to see ions on their own. That's really unstable. The ions won't become ions so they can join together with something and neutralize into this much more strong, stable compound, this ionic compound. Okay, an atom can lose or gain more than one electron. Yeah, so you can With ions, it's not just a single electron you're losing or gaining. It could be multiple electrons. Examples of ions formed by the loss or gain of more than one electron are magnesium 2+, Fe3+, S2-, N3-, etc. These ions, as well as Na+ and Cl-, are called monoatomic ions because they contain only one atom. Yeah, so these are, just note again, these are still atoms. Fe3+. Why is Fe3+ an atom? Because it's a nucleus and an electron cloud. Ions are atoms, unless it's like a molecular ion, but like the monoatomic ions are absolutely atoms. It's a nucleus and an electron cloud. Okay, with very few exceptions, metals tend to form cations and nonmetals form anions. So yeah, the chemical characteristic, the main chemical characteristic of a metal, a metallic substance, metallic atoms, is that they're more what we call electropositive. They have a tendency to want to push electrons away. Nonmetals more electronegative. They have a tendency to want to pull electrons in. Sometimes this is done fully, where you fully get rid of the electrons and become a full ion, cation or anion. In other situations, it's not like with covalent bonds. You don't fully get rid of or gain the electrons, but you just push them away a little bit. In addition, two or more atoms can combine to form an ion that has a net positive or negative charge. Yeah, so polyatomic ions like the hydroxide ion, cyanide, ammonium. These are polyatomic or diatomic, so cyanide and hydroxide would technically be diatomic. So ions containing more than one atom. Yeah, so the idea is you've got NH4. When it's neutral, you have 7 protons, 7 electrons here, 1 proton, 1 electron, 1 proton, 1 electron, etc. So with neutral, you've got, protons, electrons, you've got, 7, 8, 9, 10, 11, so 11 protons, 11 electrons. Okay, but with the ion, NH4+, you've got, you still have 11 protons, but you've lost a single electron. See? Okay, chemical formulas. We just touched on this a little bit. A chemical formula like H2O is just a description you use to describe the composition of a substance, what it's composed of. Okay, so with a chemical formula, you're describing the types of atoms in terms of elements, the types of elements that are present in that substance. But it's a little bit more than that. It's also it's like you give the proportions of those elements as well. So this here tells you that, okay, this water or ice or whatever is composed of hydrogen and oxygen atoms. Okay, but it's also, for every 2 hydrogen atoms, there's 1 oxygen atom, right? So chemical formulas express the composition of molecules and ionic compounds in terms of chemical symbols. By composition, we mean not only the elements present, but also the ratios in which the atoms are combined. Here we are concerned with 2 types of formulas, chemical formulas, the molecular formulas and empirical formulas. Okay, so with molecular formulas, molecular chemical formulas, it's just what the name is saying. It's a chemical formula like this, just like this, that's associated with a molecular substance, a substance that when you zoomed in on it, you could identify the different molecules, that's composed of molecules. That's what a molecular formula is. It's the chemical formula corresponding to a molecular substance. So if you told someone that this is a molecular formula, then you know, okay, this type of substance is composed of hydrogen and oxygen. It's composed for every 2 hydrogen atoms, there's 1 oxygen atom. But then since it's a molecular formula, you also know that, okay, this is also the number of hydrogen and oxygen atoms in each individual molecule of that substance, right? So if someone gave you, let's say, H4O2, well, you get similar information. If this was another molecular formula, you get similar information as this formula here. We know we have a substance that's composed of hydrogen and oxygen atoms. Okay, we also know that we have a substance that is, for every 2 hydrogen atoms, you have 1 oxygen atom, just like here. So we also know information about the proportion. But since this is a molecular formula, we also know that, okay, in this substance, there's these individual molecules that are built up. Each molecule is going to have 4 hydrogen atoms and 2 oxygen atoms. So with a molecular formula, you get more than just okay, here it's composed of these atoms in these proportions. You get information about the molecules themselves as well, right? So a molecular formula shows the exact number of atoms of each element in the smallest unit of a substance. In our discussion of molecules, each example was given with its molecular formula in parentheses. Thus, H2 is the molecular formula for hydrogen, O2 is oxygen, O3 is ozone, and H2O is water. Yeah. The subscript numeral indicates the number of atoms of an element present. There's no subscript for oxygen in H2O because there's only 1 atom of oxygen in a molecule of water. And so the number 1 is omitted from the formula. Note that oxygen and ozone are allotropes of oxygen. An allotrope is one of 2 or more distinct forms of an element. 2 allotropic forms of the element carbon, diamond and graphite, are dramatically different, not only in properties, but also in their relative cost. Yeah, so we've been seeing that when it comes to elemental forms of substances, we've been seeing that you could zoom in on a substance that is this, you're dealing with oxygen. It's composed of only the element oxygen atoms. Or you could zoom in on some substance it's composed of just purely carbon atoms, a substance that you would say is the element carbon. Okay, we've seen how you could zoom in on substances like this and see different arrangements of the atoms, these elemental atoms. You have O2, you have O3, right? So these different structures of the same elemental form of substances are called allotropes. Oxygen and ozone are allotropes. Diamond and graphite are composed purely of carbon. These are elemental forms of carbon, but their structures are different. It's a different substance. They're just structured differently. And like they're saying, you can have different allotropes that chemically and physically are completely different, which is interesting, right? Even though it's purely the same type of atom. Again, like diamond and graphite, right? Graphite is like lead pencils, the which you write with. All right, now just note though that allotropes and isotopes are different. 2 different concepts, right? If you had like a sample of ozone or a sample of oxygen or a sample of diamond, a sample of graphite, whatever, within those samples, you're going to have the natural mixture of the isotopes. If you zoomed in on diamond, you're going to see the relative abundance of all the different isotopes of carbon within that diamond. And if you zoom in on the graphite, you're going to see that the same thing. It's going to be the mixture of the different isotopes of carbon, which makes sense because the changing in the number of neutrons isn't really going to affect the chemical properties of the atom. Now, you might be saying, well, wait a minute, but these atoms here in the different allotropes have the same number of protons and electrons, but you're getting this different chemical and physical behavior. Well, yeah, so you can think about when isotopes are going to be much less sensitive as far as the conditions of the environment to variations in physical and chemical properties. You're getting different allotropes because you're changing the environment. Diamond is going to be formed in these high pressure, high temperature environments. But even so, it's not like when you have diamond, you get like a metal, but when you have graphite, you have a non-metal. No, I mean, it's still, you're dealing with with brittle solids, right? Not shiny and ductile, poor conductors of electricity, etc. Okay, molecular models. Molecules are too small for us to observe directly. An effective means of visualizing them is by the use of molecular models. So yeah, in addition to the molecular formula, how else can we provide descriptions of molecules? Okay, two standard types of molecular models are currently in use: the ball and stick models and space-filling models. So shown here, here's this the molecular formula, right? That's the chemical formula, but you're specifying that it's a molecule as well. You've probably seen you have these ball and stick models, and there's also these space-filling models. You can buy these off like Amazon, for example. In ball and stick model kits, the atoms are wooden or plastic balls with holes in them. Sticks or springs are used to represent chemical bonds. The angles they form between atoms approximate the bond angles in actual molecules. With the exception of the hydrogen atom, the balls are all the same size, and each type of atom is represented by a specific color. In space-filling models, atoms are represented by truncated balls held together by snap fasteners so that the bonds are not visible. The balls are proportional in size to atoms. The balls, in the case of space-filling models, are proportional in size to atoms. So yeah, in the space-filling model, the relative size between the balls is going to be accurate to the relative size between the actual atoms. And then here you just get a more accurate look at what the bonds, the actual bonds and molecules are going to look like. This would be more descriptive of what an actual water molecule would look like. Because with molecules, you've got the electron clouds are like overlapping. They're being shared, right? But here, this is not what the actual molecule would look like. This is not what H2O would actually look like. It would look more like this. You don't even have the clouds overlapping, but you can see the use of this as well. You get a much better sense of the geometry of the molecule. The first step towards building a molecular model is writing the structural formula, which shows how atoms are bonded to one another in a molecule. For example, it is known that each of the two hydrogen atoms is bonded to an oxygen atom in the water molecule. Therefore, the structural formula of water is like shown here. A line connecting the two atomic symbols represents a chemical bond. So yeah, we're still talking about molecules here. These are all molecular models. So you've got the molecular formula, then you've got these models here, more physical, visual models. But then kind of the medium between these two is you've seen these before, the structural formula, right? It's like a happy medium between these two types of descriptors of molecules. So again, when you see this type of formula, these are structural formulas of molecules. Okay, ball and stick models show the three-dimensional arrangement of atoms clearly, and they are fairly easy to construct. However, the balls are not proportional to the size of atoms. Furthermore, the sticks greatly exaggerate the space between atoms in a molecule. Space-filling models are more accurate because they show the variation in atomic size. Their drawbacks are that they are time-consuming to put together, and they do not show the three-dimensional positions of atoms very well. Molecular modeling software can also be used to create ball and stick and space-filling models. We will use both models extensively in this text. Okay, so that was about molecules. Right now in this section here, we're talking about chemical formulas. Okay, how you can write the chemical formula to represent the composition of a substance, H2O, for example, right? We just talked about substances that when you zoom in on them, you see it's a molecular substance, okay? But now, what about a non-molecular substance? Like NaCl, right? It's more of, you're going to see like a lattice. There's no unique molecules that you can identify, okay? That's where one of the uses of empirical formulas come in. So The molecular formula of hydrogen peroxide, a substance used as an antiseptic and as a bleaching agent for textiles and hair, is H2O2. This formula indicates that each hydrogen peroxide molecule consists of 2 hydrogen atoms and 2 oxygen atoms. The ratio of hydrogen to oxygen atoms in this molecule is 2 to 2 or 1 to 1. The empirical formula of hydrogen peroxide is HO. Thus, the empirical formula tells us which elements are present and the simplest whole number ratio of their atoms, but not necessarily the actual number of atoms in a given molecule. So yeah, the empirical formula, what we've been talking about is the chemical formula, is the information it gives you is, so first, the types of atoms, the types of elements that are present. So if we come back to H2O, it's telling you, okay, this substance is composed of hydrogen and oxygen atoms. It also tells you the proportion of, so there's 2 hydrogen atoms for every 1 oxygen atom. And then for the case of a molecular substance, it'll tell you the number of those atoms in each molecule. Okay, an empirical formula is only going up to the step of, it tells you the type of atoms in the substance and their proportions. That's all it's telling you. Okay, and it's important to note you can still have an empirical formula for even a molecular substance. So the substance H2O2. Okay, the empirical formula of H2O2 is HO. Right? It's only telling you it's saying, okay, there's hydrogen and oxygen in here, and for every 1 hydrogen, there's 1 oxygen. And that's all the information it gives you. Whereas the molecular formula goes a step further and tells you, well, look, each molecule has 2 hydrogens and 2 oxygens, right? So as another example, consider the compound hydrazine, N2H4, which is used as rocket fuel. The empirical formula of hydrogen is in H2, right? N2H4, it's 1 nitrogen for every 2 hydrogens. Although the ratio of nitrogen to hydrogen is 1 to 2 in both the molecular formula and the empirical formula, only the molecular formula tells us the actual number of nitrogen atoms and hydrogen atoms present in the hydrogen molecule. So you might be asking, well, why are we even talking about empirical formulas in relation to molecular substances? Because what you can think about is one of the uses of the molecular formula or the empirical formula is in the case of non-molecular substances. That's what we talked about. You don't do, for sodium chloride, you're not going to do Na2Cl2. No, you're going to report the empirical formula. The best you can do for a non-molecular substance in general is just, okay, you give the chemical formula tells you the different atoms present and then the proportions. And that's it. It doesn't make sense to go further like this. No, all you can say with NaCl is, look, there's sodium and chlorine atoms in this substance, and for every 1 sodium atom, there's 1 chlorine atom. Or like for aluminum oxide, the ionic compound aluminum oxide. It doesn't make sense to report the chemical formula for aluminum oxide as Al6O9. No. You could just say, look, this substance has aluminum and oxygen atoms in it, and for every 2 aluminum atoms, there's 3 oxygen atoms. So the empirical formula makes sense to be used for these non-molecular substances. But why are we even talking about the empirical formula in relation to molecular substances? Why wouldn't you just say, look, H2O2 instead of HO? Because this also tells you there's 1 part hydrogen to 1 part oxygen. Okay, the reason is, it talks about it here, empirical formulas are the simplest chemical formulas. They are written by reducing the subscripts in the molecular formula to the smallest possible whole numbers. Molecular formulas are the true formulas of molecules. If we know the molecular formula, we also know the empirical formula exactly. But the reverse is not true. So why then do chemists bother with empirical formulas? As we will see in chapter 3, when chemists analyze an unknown compound, the first step is usually the determination of the compound's empirical formula. with additional information, it is possible to deduce the molecular formula. So the reason is because if you don't know the molecular formula, that's why. If you're dealing with a substance and you don't know exactly what it is, but you can figure out its empirical formula, well, hey, that's better than nothing, right? But no, if you have the molecular formula, then it would be, if for a molecular substance, it would be stupid to give the empirical formula. Why? Okay. So for many molecules, the molecular formula and the empirical formula are one and the same. Some examples are water, ammonia, carbon dioxide, and methane. So yeah, note that as well. In a lot of cases, the empirical formula and the molecular formula are the same formula, H2O, right? This is the empirical formula as well for water. Okay. Formula of ionic compounds. The formulas of ionic compounds are usually the same as their empirical formulas because ionic compounds do not consist of discrete molecular units. Exactly. That's what we just talked about. For example, a solid sample of sodium chloride consists of equal numbers of Na plus and Cl minus ions arranged in a three-dimensional network. In such a compound, there is a 1-to-1 ratio of cations to anions so that the compound is electrically neutral. As you can see in figure 2.13, no Na plus ion in NaCl is associated with just one particular Cl minus ion. In fact, each Na plus ion is equally held by 6 surrounding Cl minus ions and vice versa. Thus, NaCl is the empirical formula for sodium chloride. In other ionic compounds, the actual structure may be different, but the arrangement of cations and anions is such that the compounds are all electrically neutral. Note that the charges on the cation and anion are not shown in the formula for an ionic compound, right? So for an ionic compound, any kind of lattice type structure that you can't identify molecules, you're just going to use the empirical formula. Okay, but now what they're describing here in this paragraph mainly is the fact that so when you have ionic compounds that are created, the whole idea is that they're going to come together and neutralize. That's where the stability comes from. Ionic compounds are going to completely neutralize. Okay, and so you can use this property to determine what the chemical formula of an ionic compound is. Because you know that if we look here, sodium chloride, you know that these ions are going to come together and you're going to have the sodium atom, the sodium cation, is going to be completely surrounded by the chloride anions. But then if you keep going, it's going to be like vice versa. You're going to get the chloride anions are also going to be completely surrounded by the sodium cations. So it's like it's completely neutral. And this property is going to dictate the type of structure you get, depending on the type of cations or anions that are formed. Different types of elements want to form certain ions. They want to get to that noble gas configuration. That's why you have ions with different charges, 2 pluses, 3 pluses, etc. Okay, and so for ionic compounds to be electrically neutral, the sum of the charges on the cation and anion in each formula unit must be 0. If the charges on the cation and anion are numerically different, we apply the following rule to make the formula electrically neutral. Yeah, so if you have the sodium cation and the chloride anion, and these are going to come together, well, you already have, you need the charges to sum to 0. So plus 1 minus 1 is 0, so you just get NaCl. Okay, but like if you have something like Al3 plus and O2 minus, and these are going to come together to create aluminum oxide, well, 3 minus 2 is positive 1. That's not going to work. So all you do is you just multiply you say, okay, I can take 2 of these Al3 pluses and 3 of these O2 minuses. So now 6 minus 6 is 0. So you've got Al2O3. And there's this neutral ionic compound between these two ions. Al2O3. And so the rule is, what you do is, it's saying the general trick is you say the subscript of the cation is numerically equal to the charge on the anion, and the subscript of the anion is numerically equal to the charge on the cation. So yeah, you put the cation first with its charge, the anion second like this, and then you just do this. Right? And so you're left with Al2O3. That's what they're saying here. That's the trick, which is just corresponds to what we just did before. You're taking 2 of these and 3 of these. Okay, now, but it says if the charges are numerically equal, then no subscripts are necessary. So yeah, you also want to, if need be, simplify divide down the integers to the simplest integers. So just because you have something like, x2 plus and y2 minus, well, you don't say x2 y2. No, you would divide by 2 and say just xy. Okay, so they give a few examples here. You've got potassium bromide. Is the chemical formula for this ionic compound is going to be KBr. Zinc iodide, Zn2 plus I minus, so zinc Zni2, right? And then aluminum oxide we just did, Al2O3.